All righty, folks. Hopefully everybody can hear me, and hopefully I'm here. And I literally just ate a sesame seed bagel, so nice way to start because I got a sesame seed in my throat. So anyway, hi, folks. Hey, y'all. It's Dr. Know-It-All. I'm here with Scott Walter. Greetings to everybody who is watching live, and we are going to try to track. Oh, okay. Oh, wow. I'm getting total. Hold on a sec. I think I'm getting a repeat here. So. Hold on.
Some feedback.
Well, I think it's playing someplace in the background. Sorry about that, folks. I am a noob with StreamYard. And somewhere I was doing some setup for this, and I think I had left it open, and so I was getting this.
I had that happen one time too in StreamYard. And that also I accidentally had the YouTube running at the same time and didn't understand why I was hearing voices.
I was like, oh, that's a good way to go insane because I'm here. Anyway, I apologize ahead of time because I am a complete noob with StreamYard. I've always just been on other people's channels, so I'm trying it today. We're going to do a live stream today. Scott and I are going to talk about, we're going to talk about Q-Star. We're going to talk about why Tesla might be really looking at this right now, if they haven't already. We're going to talk about why we're terrified. And we're going to first, though, give a sort of build up and talk about A-Star, 1968, by the way. I checked on that. We're going to talk about A-Star, Q learning, deep Q networks, and then Q-Star and how they all stack on top of each other, and then why OpenAI may have made a major breakthrough with this. And I'm going to sort of turn off the comments for now. I'll read them back again, but it's just to keep me from being confused because I don't have a producer like Farzad does. He has producer wife who helps him out, and I don't. So anyway, if people want to flag good comments, I will look at that. Oh, and we also have to look at encryption, which could be a major reason why OpenAI decided to table the idea and make it quiet. So yeah, we have a lot to talk about. I'm going to let Scott go first because you should talk about A-Star. And hopefully you'll be able to present. So you start with A-Star. I'll go on from there. Okay, cool.
We're going to build on that. So when I first heard Q-Star, I mean, the first thing came to my mind is like, oh, that's like reminds me. And certainly some of the papers and discussions have been talking about the two together. So it wasn't just that, oh, it sounds the same. It seems like there is some relationship, and we're not quite sure what the relationship is. I think there's a couple. One is A-Star is a really good analog to understand what Q-Star is trying to do. It could be a completely separate algorithm or something like that. The other thing is that Q-Star or some form of neural net may be used to enhance the A-Star algorithm, and hence they may have then called it Q-Star. That's one possibility. Okay. And the other is that it's neither, or it's kind of both together. So the first thing is to get everyone some sort of background and grounding on what the A-Star algorithm is, what the history of it is. And actually part of the history of the A-Star algorithm is the very first video you and I did together was we talked about A-Star. Okay. And A-Star is something that we all use in our daily lives if you ever use some sort of route planner or something like that.
So wait, did we actually, what was that first video? Now I'm
forgetting. The very first video we did, we talked about the A-Star algorithm because it's used as a route planner. It's used not just for people to be able to figure out how to drive from one city to another. It's also used by mobile robots and everything to be able to negotiate any sort of environment. And the origins of the algorithm go way back. They actually go back to the 50s in Dijkstra, where he came up with the first way of being able to solve the problem of being able to traverse a graph to get from one node to another. And don't worry, we're going to explain what all that means in a second. And then in 1968, it was kind of enhanced. And then it was, instead of being called the Dijkstra algorithm, it was called the A-Star algorithm. So
I'm going to show this because I think this is this is on Wikipedia.
I've got a better one to show. I've got a better one to show here.
Well, so I was just showing because I always talk about people going from place to place. This is actually railroads, but anyway. Okay, so I'll stop. But it's the idea of doing a search and finding the correct way to go for it.
Yeah.
So I'll stop sharing, but I thought that was a really cool little graphic. So go for it.
So what I'm going to do is right here, I'm going to go ahead and share our screen here and then just make us go away for a second. So when I was growing up, we had like
I still don't see your
you should see it. You should see something now. You see my screen?
Maybe, I gotta add you. Sorry. See, I told you I was a noob. Okay. So I just added it. There you go. Okay.
So you see this. Right. So if you've, when I was growing up as a kid, we had, the atlas of the road, the Rand McNally atlas of the United States and everything. And in there was like this section here, which was showing the distances between all the major cities in the US. Okay. This is essentially what the A-star algorithm is attempting to solve. Is a problem. If you ask a question, is how long is it going to, what's the shortest distance from New York to Los Angeles? It has to go through this network to be able to figure it out. Now, every single city on here is what you would call a node. And every single line connecting the cities is just called an edge. And it's kind of abstract. And in there, ahead of time, we already know what the distance is between each of these cities through that connection. So this is basically a priori knowledge. And you can put any information you want in there. You can put distance, you can put time, you could put cost, anything like that. And the idea is to find the route that goes from one node to some other node, which has the lowest cost function. In other words, the shortest distance or the shortest time to get there. And,
right. And let's dwell on that for 1 second. Cost function is there's two parts to the A-star algorithm. One is the transition cost, which is basically you could consider it time or gas or something like that. But basically, how much does it cost from you to go from this block to this block? But the other one is the estimated cost to get to your goal. So if you're in New York, what is the estimated cost to get to Los Angeles? And that's where interesting stuff happens. So yeah, okay.
Right. So what you want to do is if you kind of look at it, and if you were to explain this to someone and show them this network and say, okay, I want to go from one random city to some other random city, how difficult would that be? And you would start to think about it and how you'd write an algorithm, and you would come to the conclusion, man, that's just going to be a lot of, I have to try every possible combination. And a lot of people would say, well, wait a minute, this sounds a lot like the traveling salesman problem. Now, the traveling salesman problem is actually a very easy algorithm to write. Unfortunately, its runtime is like longer than the age of the universe. It is so hard to do because you have to look at every combination. So when people first looked at
this, to be specific, it's longer than the age of the universe with the
it's much
cities.
Longer. It's
ridiculous. You have to specify though with 100 cities, because if you have with 200 cities, you can do the traveling sales problem.
You can do it. You can do it with like a handful, but once you get to 100, it's like 10 to the 35 iterations. It just becomes ridiculous. And then we have more than 100 cities in the US. So the traveling salesman problem is very difficult. And so a lot of people, when they looked at it, they said, oh, this must be really, really hard. But it turns out there's some clever insights you can do in this kind of algorithm. So the first thing to remember is you have to come up with a database that represents this. So you have a couple of tables, a table of cities, and then each city has like the cities that it's connected to and what the cost function is there. And you try to descend this whole thing by going from one layer to another to another. So the first thing you would do if you want to go from New York to LA is you would explore all the connections you have. And you might start and say, I'm going to head up towards, and kind of in the Boston direction. We're going to go probably through Hartford or something like that. So you go off in that direction, and then you go up to Bangor, and then, you're basically getting yourself kind of lost. You're taking the really long way to get all the way over to Los Angeles, okay? And you can explore others. And usually what it does is it looks at the first layer, looks at those, and then keeps on going down and tries to progressively march on out there. And so the way I've described it, it seems like, man, there's just so many combinations. We are going to be going all over the place. It's going to take forever to find that route. But there are some little tricks you can do. First is you're not allowed to back up on a route you've already gone down. Once you've gone down an edge, you cannot go back up it. You just go in one direction. The other thing, no loops are allowed, okay? So you don't go like New York to Harrisburg, to Pennsylvania, to Philadelphia, back up to New York again. So you're not going to go in circles. You're going to try to get some sort of directed route. But what ends up happening is that if eventually you get there to that destination, that cost function now becomes the champion. And everyone else that you're trying to do has to attempt to beat it. And if it already is longer to take the route that goes over Boston and Montreal and Seattle than it does, let's say, the one that goes through Kansas City, then you're not going to look down that anymore. You're going to say, no point doing that. It's not necessary. And so that's one of the things that allows the algorithm to actually run reasonably well. Now, the runtime order of it is something, it's like order B to the power of D, which is maybe a bit too much to kind of explain. The idea of runtime order of an algorithm is how complex it grows, how the time grows with complexity. So if you have something that can characterize, it's got n elements in it. And if you double those n elements, the question is, does the runtime algorithm go linearly? In other words, at order n, or is it something like order n squared? In other words, if you double the complexity of the problem, does it then take 4 times as long that would be an n squared kind of thing. And it's better than n squared. Let's just say that. It's not as bad as n squared, depending how you measure it. And it's fairly quick, which is why we can actually put in destinations in our cars, and that fairly quickly finds what should be the most efficient route there. And there's a lot of other things you do. Now, the one thing about any sort of AI or database,
I think
yeah.
to put this, just to put this in context,
Mhm.
the sort of dumb way of doing this, which was what existed before Dijkstra and
Yep.
A-Star, is just to explore every possibility. So if you
Every
look at all
possibility,
the
yes.
nodes in the United States, you just try every single one. That's
Every
why
one.
it's insane. So A-Star, the big advance with A-Star is that heuristic, which is the estimated cost to get to LA
Yes.
from New York,
Yes.
or anywhere. If you're in Pittsburgh at the moment, like how long does it? So anyway, and then what you can do is you can start pruning that search tree, because you're like, well, clearly
Yep.
I just went from New York to Boston, so it's going to be longer, and I'm just going to throw away that branch of the
Right.
tree and not explore all that other stuff. So,
Right,
yeah,
right.
exactly.
Now, the other thing is that in the early days, the database basically was a list of the cities and a list of the edges and the cost to go there. And let's say it didn't really have an overview. It didn't really know the XYZ or the longitude, latitude of New York in Pittsburgh, or if we wanted to go to Indianapolis or anything like that. So that meant you may not had any sort of overview or information of what's going on that could give you a quick estimate of what do you think is going to be the best cost function. So we as humans, the solution is that you took out a ruler from New York, if you want to go to Indianapolis, and you put it along there, and you said, well, the route's going to be as close as we can get to that straight edge as we can. And that makes sure you don't start going off to Buffalo or Montreal or in strange directions, or even start heading south. And that's because we can kind of see that. And one way you can then do that is if you know the distances, let's say you know the X, Y, Z locations of these, you can do a Cartesian distance, and then from then say, I know it's 700 or something miles as the crow flies from New York to Indianapolis. So it shouldn't be more than 50% of that, let's say. So as soon as you start going down these spurious routes, you throw them out. And now what could then happen is that, remember, this A-Star is all heuristics. It's all an algorithm. What if you start to train this kind of network into an AI? So now it has kind of that overview like we have, because I don't have to show you this map or anything like that. You've got a good enough sense intuitively that I say, hey, John, what's the best way to go from New York to LA? And you'd probably say, oh, through Kansas City. They're not through Chicago.
Well,
or
certainly,
or
yeah.
like,
If you gave me the choices
would,
of like Montreal or something versus that.
Yeah. You would say, oh, I would say, it's either Kansas City or Oklahoma. There might be one of those two routes that you would know. So you intuitively know that, and that's the way you're going to guide it and go very quickly. So you could imagine if you do a mashup between A-Star and some sort of neural network, the neural network might give you that better guess, because I've tried to write so many algorithms where I look at the problem. And by looking at the problem, I can see what the answer is, but I cannot figure out how to turn it into algorithmic form, because we see the whole problem. Whereas once you get it into computer, it doesn't get the overview and be able to see it. However, I believe that large language models are able to get an idea of spatial awareness now, even though they've never seen a map or been told where anything is. Just by learning enough about the cities, they have a rough idea of the relationship of Paris to Frankfurt.
Right.
Or, London to Paris, or Stockholm to Oslo, or, London to New York. It has an idea. And so you could potentially recreate this network, because this is not what A-Star sees. A-Star sees the nodes and sees the links. It doesn't know that Boston is northeast of New York. It doesn't know Buffalo is west of New York. It doesn't have that information. But if you kind of bring that in as some additional information, then you can start pruning these trees really quickly and very, very close. So the analogy that I used yesterday is that this is very much the way chess works, or Go, is that you're in a certain situation and you have a certain number of moves you can do. And you simulate all those moves in your head to see what looks good. And then you've got to look at that move that you were thinking of doing and looking at the move after that, and then looking at all those counter moves. Now, if you have to do that every time, you're going to be very slow on the chessboard. The grandmasters, they already know which moves are good in this situation and which ones are not, which is why they're able to kind of guide their ways through. So that is
So
the
I just wanted
overview
to
of
pop
A-star.
this one back up here. Yeah, because I
Yep.
think this is valuable now to look at because you can see what the algorithm's doing. If this was a dumb algorithm, it would be going in every direction and exploring every possibility, but it's doing an explore exploit kind of trade-off. And it's exploring a route and going, is this shorter to LA than
Yes.
the other route was? No. Okay, well then prune it. So it explores for a while. There's a frontier. That's what the edge of this red sort of area is like a
Yes.
frontier area. And it's looking at that frontier and it's exploring the frontier. And then once it's like, oh yeah, these are pretty good options, then it puts those into its list of possibilities. And
Yes.
so you can see it's not perfect, but it's way better than going.
But it knows to head west. You notice it's not going northeast.
Yeah,
it's not
right,
heading
right.
up to Boston. It's not heading up
Right.
to Montreal or anything like that.
And you can
it's
see
not
that
heading
this
down
one,
to Florida. It's
right.
knowing that it's kind of this way. It's almost like a lightning bolt. You know,
Yeah.
it's kind of trying to feel the way. And then once it gets it, it knows that's the route.
Right.
So if you are lucky and you get a good, you know, you find a route pretty quickly to LA, you are
Right.
then able to say, wait a minute, try to beat this. And then you can very quickly start pruning the tree to make sure you are not going down all these cul-de-sacs that you don't want to go down
Right.
to. But as we can see, it's still kind of exhaustive. And
Right.
there are all sorts of tricks that they do. Like, for instance, you just don't do all the surface roads. You really look
Right.
at just the interstate
Right.
highways, and you look at like some major roads. There's all sorts of these different tricks that you can do to try to improve
Yeah.
it. But still, A-star takes a little bit of while to do the searching, even though it's much better than a full exhaustive search. So
Right.
the way A-star is kind of formulated is that you would say that you're calling some function, and it's called A or A-star, and it has two parameters. One is your start location and your destination, and you want it to return the route.
Right.
And one of the things, of course, you can do is when the route is returned, you can cache it for future use. So you don't go
Right.
through it again because it may be there. But in many cases, it's going in there as if it's never seen this map ever before. You know, boop, oh, I've got some database loaded in here. I run the algorithm. I have to come up with the answer, and you get that. So you have a starting
Right.
and then a destination. And the A-star is the idea is that you're coming up with the optimum, the best route. Don't just get me any
Right.
route, but actually get me the best route, provable best route. Now,
Right.
Q-star, I think, is attempting to do the same thing, but it's
Right.
using,
Well-
rather than start and destination, it's using state and actions.
Right. Well,
And then
except I
flipping
mean,
over-
A-star uses state. I mean, it's just state
Yes.
is sort of rolled into it because
The
wherever
state
you are
is
your
like
state.
where you currently are is
Yeah,
your
where
current
you are.
location.
Yeah.
Right.
Yeah, yeah.
Whereas
So-
if you abstract it more to Q-star, state can mean anything.
Right.
It's
Right.
whatever the state of the machine is. And then there's these actions that you can do, and the actions are going to result in some sort of activity. And the question is defining an output or a result of your actions that are going to be optimal. And
Okay.
again, I like using the example of Doctor Strange. You know,
Yes.
it's like that one scene in the
Right.
Avengers where he's sitting there and he's simulating all the possibilities,
Right.
trying to find the best one. You see, he's got to go through like, I think it was like 4 million something different scenarios of what they have
Right.
to do. And there's like only one that works.
Right.
So Q is trying to do the same thing, looking at, all right, I'm right here. What's the best result that I'm going to
Right.
get? And how quickly can we do it? And I think that's
So-
the key,
so-
is it does it really fast.
Right. And this is where I had ChatGPT help me, and I would have had Grok help me, except I still don't have access to Grok. Hint, hint to the XAI team. But anyway, it's appropriate because it actually should be ChatGPT helping me out with this. But I mean, I knew this, but I didn't have a good way of putting it. And this I thought was a really good explanation. And I go on down here. So it did a terrible graph, but anyway, or a picture. So anyway, Q learning, deep Q learning are both reinforcement learning techniques. They're used for training agents. And I think this is a really important word. So table that, hold on to that word, to make a sequence of decisions to achieve a goal, usually in the context of a game or a simulation. So that's the traditional context of this. Traditional, like it's a couple of years old. So anyway, so Q learning. So if you remember, you've got your A-star algorithm has your transition cost, which you pretty well know. It's like how much time, how much distance, whatever it is. Distance is easy, right? If you're going from one place to another, you know how many miles or kilometers it is from this city to this city. The thing that is interesting about A-star is that heuristic, which is that a person has to use their knowledge, their domain specific knowledge to determine what it is that's that cost to get to the goal, the estimated cost. So where Q learning and deep Q networks come in is figuring that part out. It starts to figure out the heuristics for you, which is good because in a lot of situations, it's really difficult to know what the heuristic is. So anyway, so you've got some your environment and your agent. So your agent is your thing, right? Where your piece that's moving around through this world, or your car or something, and it interacts with an environment, which is a Markov decision process. Don't even worry about that stuff. That's not important for this discussion. And then the Q value, the core concept in Q learning is a Q value or action value, which represents the expected, so this is the heuristic part, future rewards for an action taken in a given state. So again, a reward for driving, I think it's just very easy to understand that, is that it will take you the less time or the least amount of time or the smallest amount of miles. And oftentimes, like I think in Google Maps, you can set those two options. It's like a toggle. You can be like, I want least miles or least time. But anyway, so let's just assume least number of
You can
miles.
even do energy, most energy conservative and everything else. You
so
can
you
do
don't go
things
over
like
mountains and stuff.
least altitude change, because if you're towing, you'd want to know that exactly.
Right.
So
so there's a lot of stuff.
You can come up with all kinds of cost functions. Yes.
Right. But so the cost function, we're just going to define, again, that's the kind of heuristic thing is, well, the cost function is we don't want it to be any more miles than it could be, and we're going to go simple. But anyway, it figures that out. And then the algorithm maintains a Q table with Q values, which would look like something like this. You've got your state and you've got your actions and you've got your expected reward for each of those actions. So that's kind of where you are. So it has a Q table, and then it derives a policy from those Q values, which is, what am I going to do? So agents have policies. Agents are like little mini people, and they have desires, and they have policies, and they figure out what is the optimal policy to take going forward. And then the update rule is this math. And again, it's not important for what we're talking about here, but it's not that complicated, honestly. It's just a few basic factors and some multiplication and addition and stuff. But you figure out the new state.
It can also be the combination, because what does it mean to be optimal? So it's pretty clear when we say we want the thing with the lowest mileage. But it could be, well, I want a combination of lowest mileage, but also, or best mileage, best time, and best economy, or something like that. And so you have to have some sort of weighting function. Might say, well, you go a little bit further out of your way, but the time might be better, and you'll actually save gas on it or something.
I think if you look at that, you can easily see that. If you look at a map, like say just wherever you are, take a Google map thing and find something across your country from you, and then look at all the surface roads. And if you mapped it out, you could find a shorter distance taking surface roads, but it's going to take the highways, because the extra distance that you go on a highway versus taking the absolute shortest road is completely compensated for by the fact that you're not going through a city. You have faster speed limits. You don't have lights and things you have to deal with. So obviously, so yes, you're trading off time for mileage, clearly in that case. So
yes.
So anyway, the big important part about this is that it's a state update, which is exactly what A-star does, is that you have a new state, and the new state is figured out by taking the current state and estimating what the cost of going in any given direction is, and then figuring out the optimal next move, basically. So it's just a better way of doing A-star, but with agents and things. Anyway, and then we get to deep Q learning. And so previous to this, we don't have deep neural networks in Q learning. It's just creating a table, and a human, Scott or I could be like, oh yeah, I'm estimating the action will give us a 0.7, whatever that means. But in this case, deep Q learning is using a neural network to figure out the table. To approximate the Q values, the approach is particularly useful in situations, and this is very important too, with a very large number of states. And this is where Q star is going to come in. So large numbers of states means a game of chess even has a large number of states, because it's got crazy amount of stuff. Go has a large number of states. Reality of any kind, large language models / driving, any of that kind of stuff has huge numbers of states. So this is where things start to really become important, because A-star is going to suck at that. It's just not, the order is, it grows too quickly, and so it just can't handle that kind of stuff. So anyway, so then you have neural networks, and that predicts the Q values. And then there's some other stuff. There's target networks and experience replay, but that again is not important for our discussion. And then it did a terrible graph here, but basically, so you've got this idea of a Q table, and then you can update the Q table to create a new Q table, which changes some of these values based on how you just moved. So that's essentially what's happening, but you're using a neural network to do this instead of a human being to do it. So that's basically what you're doing. And then it has an idea of a Q star, but this is not the right definition. This isn't from the paper. This is actually an optimal. So star usually means like optimal in this kind of context. And so Q star is like the optimal way to go. But I think in the context of the paper, and I want to bring that up next, it's a little bit different. So, all right. Do you have anything to add to that? Or because I definitely want to talk about
I think that's right.
Yeah.
So you just the Q would be a way of being able to go from the current state to maybe some result, but it's not necessarily the optimal one. And the Q star is searching over all possibilities and then finding what's the best one. And the problem is if you're searching over all possibilities, it takes a long, long time. But if you can come up with a way that's very, very efficient, then that just accelerates everything a lot. And what I've seen what people were saying, they're talking about a couple orders of magnitude faster than A star is trying to do something similar to this.
Right.
And the question is where's the application of this going in? And so it turns out that A star is probably not a bad analog to what Q star is. It may turn out that not only is it not a bad analog, but it may actually be that it is used sort of in the learning context, and then Q star is just putting it on steroids, so it's able to find that answer really quick.
Well,
you and I looking at that map, all the possibilities, and we saw how that search map was going. You and I would like quickly say, no, I would just go right through there, and we'd come up with a really good guess. We could then give that to A star, and A star could go through and confirm that pretty quickly that that's your best guess without going off all over the place. So that's where intuition kind of comes in. And what it seems to me is like Q star is a way of replacing a heuristic with more intuition about the problem because it understands the problem. Again, this idea that large language models have no idea what a map is spatially, yet from reading enough stuff about the relationships that different cities have, it's able to reconstruct that in science. So that's information it was not actually given, but is derived information. It's understanding of what's going on. And again, you can then use that to intuit what is going to be the best possible solution. And then you can just focus on that and then find, well, it's not exactly that one, but just a little bit to the side is what's actually the best one.
Right. So yeah, let's turn to this paper. I think this is where we're really starting to get into the meat of this, because this is Adrian Dittman found this. So good for you, Adrian. Thank you for finding this. And then Stephen, but it was Stephen McAleer who's one of the authors on this paper, wrote about this when people started talking about Q star the last couple of days. He's like, hey, we got there first. And so this is Agostinelli et al. From March of this year on Archive. I don't know if it's been published anywhere else, so peer review, whatever. But anyway, I just have some highlighted sections and I want to show this, and I'll leave a link to the paper in the description. I don't have it in there right now, but I'll do it once this is not live anymore. But anyway, so yeah, A star search, important, obviously. The problem is that the computation and memory requirements grow linearly with the size of the action space, which sounds good, but it's not as good as it could be. The burden becomes even more apparent when A star search uses a heuristic function learned by computationally expensive function approximators, such as deep neural networks, which would be deep Q networks. So anyway, they're like, this is the problem. We're going to solve this using Q star. So.
And again, go back to the title for a second.
Oh yeah,
that title is intriguing.
Yeah, right. A star search.
A star search without expansions.
Right.
I mean, that right there tells you everything you need to know. So again, it's like playing a game of chess and you're in a certain position and you have to consider every single possible outcome. However, a grandmaster, he's already seen that situation.
Right.
And he knows that this is the right move. Doesn't have to expand or go down anything. It just knows that's the move that you're going to go ahead and do. So this is intriguing that, wow, how can you do a search without expand? There must be a little bit of expansion, but it might be just talking about, not this really large expansion that you have to do, which not only takes time, but takes a lot of resources because basically you're going, down a tree and then having to come back up a tree and doing it again and again and again. That's exhaustive.
Yeah. And that's that. If you go back to that little thing that I showed of the US with the train networks, it's like you see it spreading out. So it's expanding and it's going down this route, and then it's like, nope, that's no good. And it goes down this route. It goes like, no, that's no good. And it's like, oh, this one's pretty good, so I'll keep going there. So
Basically, it's like
that kind
slime
of idea.
mold, is what it's
Yeah,
doing.
it's like, it
Slime
is.
mold
It
is
looks like
moving
slime
towards
mold.
something, going after different directions. And then once it finds that route, suddenly all of those tendrils die off and it just, whoop, that's the way you want to go.
Right. So anyway, it's learning heuristic functions with deep Q networks and A-star search. So obviously they're related to each other, which is why we've been talking about this. So anyway, we're going to jump down, look at a couple of tables and graphs and things like that. Again, read this if you want to. It's relatively deep, but I'm just trying to get in here. So RC is Rubik's Cube and the number of meta parameters they've gave it. So the first one is very, very small, just with 12 and then 156 and 1884. And I believe that's the number. It's like a giant meta Rubik's Cube with like 1884 faces. So imagine like a huge one that you have to solve, right? So I think, anyway, something like that. I could be wrong about that, but the idea is that the 12, 156, 1884 is massively more complicated to solve as you get to each of these things. And of course, the traditional boldface, the Q learning is iterations per second. It's much faster, and the training time gets absolutely nuts versus kind of a standard. I mean, when you look at this when it's small, they're pretty comparable. I mean, Q learning is a little bit faster. But look at this when you get to 1884, we're looking at 0.4 iterations per second using Davi, and it takes 347 days to run this algorithm. Whereas the Q learning algorithm, their Q star, anyway, it takes 2.7 days. So it's the difference, the gap just becomes massive when it gets really, really complicated. So anyway, then you've got, and there's an interesting thing here where actually A star is faster for Rubik's Cube 12. You can see it's just a little bit faster here, but that's a toy problem. It's very, very small. And the whole point of this is when you get to really, really, really big search spaces, this operates just outstandingly well. So what you really want to look at is this over here, like these guys. Whoops. Anyway, these numbers over here are where you can see that you're looking at 1288 nodes and 280 anyway. So it's just way, way faster with that. And
that shouldn't be a surprise that when you start getting things that are very complex, that your algorithms are not going to be as efficient. But when they're small, the algorithm will probably beat anything else. So if you remember from being able to like invert a matrix, there were some very straightforward closed form ways of doing it that are very precise and very easy, using something called Cramer's rule, which is not meaning the inverse Cramer or anything like that. Right. But it's a straightforward way of being able to do like a 3x4, 4x4 matrix. But once a matrix starts getting big, like 6x6 or 8x8 or way beyond that, then suddenly you start using Gaussian's rule or to be able to do the elimination, LUD decomposition, because it's much faster. And so you end up finding that depending on the scale of the problem, an algorithm might be perfect and even preferred for something very, very small. Right. But once you get complexity, you have to bring in something else to be able to solve it. So I'm not surprised to see that, the traditional way is still going to be faster when it's smaller. Right. But at some point, it takes off.
Yeah. Yeah. And so again, you can see down here, there's some boldface stuff that shows that Q star is outperforming by a significant margin the sort of more traditional stuff. So anyway, there's a whole bunch of other stuff. This table shows that though the RC 1884 has 157 times more actions than RC 12. So in other words, much, much bigger search space. Q-star only takes 3.7 times as long to find a solution and generates only 2.3 times as many nodes. That's what this table up here is. So this is pretty outstanding. Whereas A-star, on the other hand, takes 37 times as long and generates 62.7 times as many nodes. So A-star is growing. The whole point of this paper is, look what we're doing. We're guiding the search, right? The whole thing about this deep Q network is we're not just like randomly guessing. We're doing a better job of that heuristic. Rather than just kind of going like, well, head southwest. That's generally the right answer to get to LA from New York. You're giving it what you probably want to do is look at getting on an interstate first. And then you want to think about maybe going through Philadelphia first, or maybe avoid that, going on a bypass, so it'd be like if you were telling a person, you could just Scott goes like, hey, John, how do I get from my house in Tampa to your brother's house in Manhattan Beach, California? And I'd go like, just go west. And you're like, oh, great. And so Scott's driving
Mhm.
into the ocean, and then he's like, well, that's not going to work. And then he's like, I got to go up the ocean,
Got to go up.
But if I gave you a lot of information and I said, okay, you want to do this, you want to get on a highway, you want to go north first until you hit the 10, then you want to go west, I
just
can
stay on the 10. I mean, yeah. Most people
just
would know right away.
10.
Yeah, just get up to the 10 and you're okay. And then you just figure out how to get there. Exactly. And again, that's because you have some sort of outside knowledge, or you've been able to get like an overview of the whole network. And you've taken that whole network and you've kind of compressed it in some way that now you have this kind of intuition or feeling that this is the solution that you want to have, because you see the big picture. Whereas A-star never really sees the big picture. It just more or less knows that this node is connected to these nodes, and I've gone down this tree, and I know what the cost is if I go off in this direction, and now I want to try another route and keep on comparing and comparing and comparing.
Yeah, it's I think that's actually super good to dwell on for a second. It's so A-star, what A-star sees, again, I'll just use New York as an example. It just sees Boston 200 miles, Philadelphia 145 miles. What's another close one? New Haven, whatever miles, right? So all it has is, it's like, I'm here and here's a bunch of distances, but it's great. It goes to Boston and it's like, well, let's say Boston was, no, New Haven. So let's say New Haven was only like 57 miles, and I'm just pulling these out of my butt. But anyway, it goes there and it's like, cool, that was only 57 miles. That's the shortest distance. Well, as it turns out, any human would go like, well, that's the wrong direction, dumbass. So, what are you going that way for? But the problem is that A-star's dumb. It has to get to a point where it realizes, oh, now I've had to go around the horn, and, and that's like, oh, now this is super long. So that's a bad way to go. But with better heuristics, and this is what these deep neural networks are doing, these deep Q networks, they're going like, well, let's do a better job of understanding where we are and what's happening and what the state is and what the expected outcome is, so that we can get you there faster. And that's kind of the goal of this whole thing. So, oh man, it didn't take my, I had these highlighted here. So I guess for some reason, anyway, so this is important here. As the size of the action space increases, Q-star becomes significantly more effective than A-star in terms of solution time, which is important, and the number of nodes generated, which is super important, because eventually you run out of memory. And there's a couple of graphs up there where they're like, A-star ran out of memory, so we don't have like data for it, because it just was like, can't do it. Doesn't matter how long
it gets crazy, because you have to cache like all those routes so you can start to compare them. Because it turns out if one route is the best route, well, then you need that information to how you got there.
Right. So anyway, and then it talks about how the small spaces, but we don't care about that for this discussion. But in the largest action space, Q-star is orders of magnitude faster and generate orders of magnitude fewer nodes than A-star, while finding solutions with the same average path cost. So, so you have to run these simulations a lot of times to get an average, of course, because just one time it might get lucky. I mean, maybe it just picks the exact right path, and A-star's like, did it. It took me one shot and I did it, but that's very unusual. It's not going to happen very often. So anyway, you run it a bunch of times and you look at the average of this. And so this is a significant improvement here, right? And then so anyway, Q-star here uses a deep Q network to eliminate the majority of the computational and memory burden associated with large action spaces by generating only one node per iteration and requiring only one application of the heuristic function per iteration. And it's really interesting. What it's doing is it's actually estimating the, and I had this highlighted. I'm going to see if I can find this. Let's see. Architectures could be modified. Shoot, it has a whole bunch of things, but where is that? So sorry, I can't find it, but basically the idea is it doesn't even have to know all of the different pieces of the path. It just knows the general, if you take this action, this is going to be the cost overall. It doesn't have to calculate individually. So it's very cleverly using the Q table to just sort of summarize it. So it's just guiding. It's just like, this is a good guess.
Yeah. So again, you want to go from New York to LA,
right?
And it's like, clearly you don't go over Seattle, go over Kansas City.
Right.
Now we don't know all the steps in between there, but we know that's going to be better than going that other route. And so
Right.
once you have that guiding principle, you can then go ahead and fill in the details as necessary.
Right. And this is also important. I just want to call this out here really quick. QStar can solve problems with dynamic action spaces by choosing a DQN architecture that uses structured prediction. But the important part here is dynamic action spaces. In other words, it doesn't have to be static. It's not a maze algorithm's a great one. That's a static one, right? So you got a bunch of spots you can't go. So what's the fastest way through the maze? That's just static. But everything in reality, language is dynamic, driving is dynamic, talking to you is dynamic, all of this kind of stuff is dynamic. And in the dynamic action space, it has a distinctly, it is able to deal with that dynamic action space.
Yeah,
So
right.
that is
and,
really,
and
really
again,
cool.
if we go to QStar, or
Right.
sorry, A star, when it's looking at the network, the whole assumption is that that network is static, that we've loaded all the data in there. We've calculated all the distances because the cities don't move around or something like that. And if you're just looking at it from a distance standpoint, that's fine. But if you're looking at it at a time standpoint, that's changing, and that's changing all the time, partly because, suddenly maybe they've built a new roadway that's suddenly going to be a bypass, which is going to make some a lot faster. So now you've got to consider that in there. You've got to add that in. And of course, dynamically, all the time's changing because of construction, because of accidents, because of traffic and everything else, that suddenly what seemed like the quickest path is changing, which means you have to constantly be able to reevaluate it. Now, It's fairly easy to reevaluate it because you already know what's the way you want to go to LA. And it's not like you're suddenly going to decide, whoa, we're going to go over Seattle right now. It's a bad idea to go in the direction of Philadelphia or something like that.
This, by the way, sounds like something I would do. It's like there's a traffic jam. I'm going to go 100 miles out of my way to avoid this traffic.
Or in this case, like probably 2,000 miles out of your way. So it's going to be roughly along that way, but still, the example of the roadway network, it changes a little bit. But the state of the world that you would be typically going through could be changing a lot because everything is moving around. So you're trying to avoid these different obstacles. And at one instant, you can look at all the obstacles, but the next instance, all those obstacles might just start moving around really quickly. And you have to come up with a completely different decision map.
Okay, so let's take a moment because I see there's a bunch of comments and I do want to look at those,
Mm-hmm.
but let's take a moment to talk about consequences of this. So this is a paper from March. Again, I should have said this at the beginning, but this is all speculation. We're going to be wrong about some of this stuff. It's quite definite. But the speculation is that OpenAI has taken this and they've run with it and they've figured out how to utilize this in at least language, maybe multimodal AI stuff. So GPT-5 using QStar. What that would allow it to do is to operate much more efficiently memory-wise, to get to an answer faster. And again, another part of this whole thing is this math thing, where it apparently got 100% on like sort of grade school, middle school math, as opposed to like 80% or something. And that doesn't sound like a lot, but it's huge. To get 100% is absolutely stunning with something that is a statistical entity.
Let's bring in like Pareto's rule here. So usually to get up to 80% requires 20% effort.
Yes.
And to get from 80 to 100% requires 80% effort. So the last 20% requires more effort than everything else. So you may not think, oh, it's very much. Like, nope, that's where all the effort is going in. So that is something really big.
Yeah, it's huge. And it's a lot of it has to do with just the way that neural networks work because they're statistical and statistics doesn't answer math problems because there's no creativity. I mean, I take that back. People don't get on my case, but what I'm saying is 2 + 2 = 4. And that's just, you're not being like 2 + 2 = 4, except sometimes it's 4.5. And that's what a large language model will do to you is it'll give you an answer that most of the time is right and not sometimes. And it becomes harder and harder the more complex the math becomes because you have to follow the chain of thought. So anyway, so the deal with this would be that this QStar would be a guiding type of thing where it would say like, no, these are the better possible solutions. Examine this solution space more closely. This is probably the right thing. And then it's always easier to check your answer than it is to come up with something. That's another. I don't know whose rule that is, but that's an important rule because it's one of those like, it's pretty easy. You can say like, hey, is this right or not? And you do all your math and stuff. And then it's fairly easy to go through and go like, nope, you multiplied wrong here. And so, that's a lot easier than coming up with the original solution. So anyway, That's one piece of this. Another piece of this is that this, as I said at the beginning, has agents, and agents reinforce themselves. They learn on their own. And this is the kind of thing like Alpha Zero did, where it played itself who knows, 10 million times in Go and suddenly became way better than the best Alpha Go player in the world. This is doing this, but potentially in real life, not in games. And it's like infinitely harder to do that in real life. And that's terrifying, because if these things can learn on their own, create their own data, learn the optimal things, and do it in a memory efficient and very computationally efficient way so they can do it quickly, that means that there's the hockey stick thing. So you're going kind of flat, and then all of a sudden it's like, phew, and it just takes off. And they might have gone like, uh-oh, it just went, the hockey stick just went straight up. Scott's looking at me like, yeah, it's scary.
Yeah. I'm just thinking that, with the old saying, follow your lodestar. Now you're saying follow your Q star, which is basically what's going on. So that is your guiding principle now. So follow your Q star.
But I think the TLDR of this is that Q star, if it's working the way we're guessing, is that it might be cutting humans out of the loop, because the whole thing about this has been reinforcement learning through human feedback. So there's been this human feedback in the loop where we're the ones providing the heuristics. Basically, that's what the human feedback is like, yeah, I like this answer better than that answer. That is us providing heuristics. But if the computer doesn't need us anymore, we're super slow. The computer can go way, 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 way faster than we can. So it's just most of the time sitting there waiting for human feedback. If it doesn't need human feedback anymore, that's a big deal. And then agents is a really big deal, because I'm very careful always to be artificial general intelligence is a tool. It's a very general tool, a very cool tool, but it doesn't have any desires of its own. Agents, on the other hand, are a whole different matter. That's the, I'm sorry, I can't open the pod bay doors, Hal or Dave. That's the kind of situation we're getting into if it's an agent. And then do you want to talk real quick about I can't remember the number, but the encryption standard, it's like AE something or other. This is another piece of the puzzle. And okay, so I'll just talk about this really briefly, but somebody brought this up on X this morning.
I saw that too. Yep.
Yeah. And basically there's an encryption standard that is unbreakable. They're like quantum computers someday might be able to do it or something. And another hypothesis here is that this Q star thing learned so quickly and became so good that it broke it. It was just like, oh yeah, I can figure out what this encryption is, and I'll tell you what the plain text is. And if that's the case, then all of our banking, all of our security, like everything is moot. And that could, if you think about that, OpenAI, Ilya Sutskever, Sam Altman, all of these guys could have been like, holy crap, this is a really significant problem, and could have had a falling out about that. Yeah,
exactly. Wow. Scheisse. That's
that's terrifying, right?
Whoa.
And also a reason why the board might not give a public reason for doing this. They might be like, nope, we're not going to tell anybody because we don't want anybody to know. But if we're guessing correctly, and who knows if we are, it doesn't matter whether they tell us or not, because now that people know the steps to get there, somebody else can solve that problem. And so that's really scary.
But then doesn't it work kind of both ways, that if someone is like basically able to break all of your encryption, you can probably figure out where the attack vector was coming from, because whatever that thorny wicket is that you're trying to go through, it's like, that's coming from there. So it may be easy to break into someone's house, but you might also be able to prove that you were the one that broke into someone's house. Just like that.
Except the problem is, if they can break this stuff and they can do it relatively quickly, they just take everybody's money, and then what does it matter whether they caught or not? It's like
I'll take it back from them. That's exactly. So
but that's okay. I'm just thinking. I'm talking about mass scale attacks.
Mass. But it's almost, was it David Brin with his book? The whole idea is that everyone knows everything about everyone, and so we're almost at that stage,
right? It also makes you wonder, and I haven't thought about this, I'm thinking about this in real time, but it makes me wonder about blockchain versus this. Because one of the things about blockchain is it's work-based. So so they have to mine in order to solve algorithmic problems. I don't know. It could break blockchain as well. I'd have to think about that more.
I think the only thing it comes down to is that if I understand right, what it really makes Bitcoin unbreakable is the amount of energy that you need to do it.
Right.
So
and I think that's
basically what it is that if you have a limited amount of energy, then this becomes very, very hard. So it's something you can break. It just takes a lot of time right now. And the question is whether QStar could do that any faster. That's an open question. That if it does, then it breaks it. But if it's still the type of thing, it's like, nope, you're still going to need, incredible amount of computing power and a lot, and the energy that goes in it. Because that's the whole thing is you can have as many chips as you want out there, but if you don't have the power station to run those chips, then you aren't able to do anything.
Yeah, but let me throw out a devil's advocate situation here. And that is, let's say that this thing figures out. So the whole idea is you're mining something. You're trying to solve a very, very intractable problem, and it takes a long time and a lot of compute power. But if this thing, even if it can't figure it out instantly, if it can figure out, say 10% faster than everybody else, that means you use 10% less energy, 10% less compute time. And if it's half as long, then you, holy crap, but any kind of advantage you have in that is going to give you an outsized advantage.
Yeah, that's sort of already happening already, because you have people that bought those GPUs like 5 years ago when they do Bitcoin mining, and then suddenly they're like useless. Yeah. The next one's kind of come along. So it's just like another kind of version of that. It's just that whether that becomes democratized and have enough, and then the question is whether someone is then able to somehow get 51% of the compute on the blockchain, and then that's when it gets dangerous.
Yeah. And of course, people are, there's a lot of stuff going on in the comments right now about blockchain, but it's basically proof of work. But if you can cheat the work, in other words, if you can work smarter, not harder, and solve these problems any faster than the basic model, then it's going to give you an advantage. So let's take a look. Knock on the door.
But I guess all it does is it means, see, this is where it really comes down to. If you're just getting the proof of work quicker, that just means you're able to hoard more and more Bitcoin. But then there's the other, is that if you end up having enough nodes on the Bitcoin, on the blockchain, and then you can go in and you can surreptitiously change things, because in the end it comes down to, okay, here's my proof of work, and then that everyone else agrees, oh yeah, your proof of work is right. But it's like, no, we're really cheating. We're making everyone think the proof of work is right. We're able to then insert something. So then it just kind of comes down to whether that would allow you to change the blockchain because you dominate such an incredible amount of the compute that's out there.
Right. Hey, Faye, by the way, has posted some interesting stuff, but I don't know, Faye, if this is true or not, but she says that Grok plays physics games. So I don't know, since I don't have access, but that's actually really cool. So that would be really interesting. But I'm sort of looking through here if there's any ideas for this. Yeah, a lot of people are on the blockchain idea. So really interesting. QStar is the beginning of the end. Yeah, that's the kind of thing I think about, is that QStar could be the beginning of the end here. It's very it's I don't know. There are potentially terrifying consequences to this. And I have always been very careful to say, like, AGI is scary in the hands of bad actors. AIA, which is artificially intelligent agents, are scary on their own face, because they're just like, they have their own desires and we don't know what they are. AGI right now has no desires. Like, I can open up my Chat GPT window and I can let it sit there for a month and it won't do a thing. It has no desire. But an agent, once you create an agent that has its own desires and is acting in the world on its own, that's a whole different matter. I mean, what if you told, if this thing hypothetically existed and had not broken, what is it, SHA-256 or whatever the big standard of encryption is, if it hadn't broken it yet and you just said, hey, yo, go and solve this problem and figure it out, it probably would do it. It might take a little while, but it'd probably figure it out. It would say, like, okay, that's an agent that's just operating on its own and figuring out how to do that. By the way, just this totally random side issue, but I think it's really cool that there has been a lot of work recently called trading time for accuracy. And that's a cool aspect too, which is basically that when you're asking ChatGPT to generate the next word, you're giving it a certain number of microseconds or milliseconds to do that. So it's like, do it now, do it now, do it now, do it now, that kind of a thing. And what they're discovering is, if you say, like, no, take more time, now you have like seconds to generate each word or whatever your thought is, take as much time as you need. It comes up with way better answers. So you can trade time for for much more precise answers. And the way they're doing that, interestingly, is similar to this, Scott. So it's going to circle back to A-star. What you do is you generate multiple. It's like a little bit of a Monte Carlo thing. You generate a whole bunch of possible answers, and then you check the answers to figure out which one you like the best, and then you work on that. So it's very similar to A-star here, and maybe Q-star. So
yeah, and that already kind of freaked me out. That I think Robert Scoble was one that was saying he gets much better answers that when he puts it in there and he just says, and take a breath.
Yeah,
and
yeah,
it's
take a
just
breath.
like, what's that got to do with it? And then he says,
that,
it's much better. And the speculation is like, wait a minute, does that mean it really kind of understands itself and how it operates and knows that you want me to kind of do this or make this adjustment or go into a for loop a few more? To me, it just seemed kind of weird that making some sort of statement of like, take however much time you need to be able to do it actually tells it to go in deeper, which seems to be a really interesting hack, or that, almost like the self-awareness that chat has about itself. And to me, it's kind of a head scratcher. That's like, really? That's all you have to do, as opposed to like some temperature setting or something else that you would think you'd explicitly do.
Right.
Just a random piece of text is going to be enough. Now,
well, and show me your work does that too. So yeah.
Right. But some of the other things is that if you kind of restrict it on what you want the output to look like, that sort of helps. So if you say you want it in the form of a Shakespearean sonnet, then, it does have to think a little bit harder on that. Or if you want it, write it like Hemingway, it'll do the same thing. But that's one thing. The other thing is to say, take a breath. All right. Why should that affect the output at all? But it seems to.
Right. Yeah. No, and I think, where is this? Alahum, I guess, said, take a breath and think in steps brings me better results. So those two things together, but those are related to what's going on here, because a lot of what's happening and a lot of the rumors around this are that this Q-star thing it has an awareness of itself. It's able to, again, because it's an agent, it's like, oh, that wasn't great, my solution to this problem. It'd be like, again, New York to LA, and it's like, it found a way, but it's like not that good. And it will evaluate itself and say like, that wasn't great, so let's try again. And so at that point, it's able to update itself. It's on its own and say like, yeah, let's make this better and make the architecture better and make the predictions better, because it's able, I guess, to alter that deep Q network, that table that it's got, effectively a table that it's using to figure out what the heuristics are. And if it can update the heuristics on its own without a human in the loop, that means that it's able to then improve itself. So there's a level of self-reflection going on, which is really interesting.
Yeah, it can be interesting that you drive a particular route, and even though you say, okay, just give me a route and it gives it to you, it's still thinking about it. It's like, I'm kind of it's nagging idea here. Is like, is there a better way? And he keeps on thinking about it and thinking about it. And then you go to work and you're like that. And it says, hey, John, you know what? I've been thinking about this all day. It's really been bothering me. You know what? There's a better way. And the better way is to go through your mall, like what you do or something like that. Yeah. And that would be kind of crazy that if that agent just never kind of stops, that once you make that query, it just keeps on thinking about it. And we as humans sometimes are like that someone will ask us something, we'll give an answer, and then we'll wake up in the middle of the night and say, whoa, wait a minute, I've got a better idea. Or like, again, you get this nagging suspicion that there's some other sort of answer. And sometimes it'll just pop up like a month later, suddenly go, oh, remember you asked me that? I just thought about that. This would be a better way. Right. Do you think it's going to start doing something like that it's just going to keep on processing in the background?
Well, this is actually Tracy's comment here is really interesting. It's okay. Take your time. So yeah, I don't know. It seems like it already kind of does that. And remember, we're talking about GPT-5 or something at this point, or Grok 2 or whatever. So the potential is that we will get that sort of explicit. It sounds like people are making good progress. It's really interesting. Andre Karpathy, did you watched his talk, right, on large language models? It's a really good talk. Just search his YouTube channel, or X. And he said specifically in this that algorithmic improvements are not that important. It's all been about how much data you can throw at the problem, and it just keeps getting better. But my opinion is that we're missing a major algorithmic breakthrough, or maybe we're missing an algorithmic breakthrough that we need to jump to the next level, because these, it's learning, but it's not learning that fast. But holy crap, if this is that algorithmic breakthrough and it can improve efficiency, reduce the compute cost, reduce the memory footprint, all of that kind of stuff, and make it self-aware, that's just huge. And I do want to turn to Tesla right now, because full self-driving, if the Tesla AI team hasn't looked at this previously, everyone's ears probably perked up when they heard about this stuff and the rumors, because they were probably like, wait a second, what's the most complex thing in the world? Reality. And so here, talk about a gigantic solution space that you have to search. If there's a way of reducing the problem is heuristics, and how does it figure out the heuristics? But that's what the deep Q networks are. So basically, you're training a teacher. You're saying, here, learn about the world, figure out what the best possibilities are, and then go and train the student. So I guess as an analogy, that might work. I don't know. Does that make sense? Yeah. Okay. Yeah. So cognitive scientist. Sorry, I'm looking through all these things at the same time. I need a producer. Sorry, folks, if I'm missing good comments. I'm trying. So yeah, John Gronk. Okay. I don't know if you've seen anything in there, Scott, as well. All right. Yeah. This is kind of an interesting one. You're training your replacement. Yeah, we kind of are. I think that's been true for a while, and it could be true.
Yeah, I'll be taking over the channel before John knows it. Yeah.
I don't think he's talking about, well, okay, fine.
I wasn't talking about me.
Yeah, we have virtual Scott and virtual John.
Yeah, exactly. Both of us are going to be replaced here.
Yeah. Eventually, I won't have to do anything anymore. I'll just be like, hey, come up with a video for today, record it, make it look like me. That'll be awesome. Anyway, it's already happening. That's the scary part. Elon in FSD, fun. Yeah. So full self-driving 12, full stack. Who knows if this Q star stuff, it just seems like, I don't know. It's interesting because Q star in this circumstance is generative, in the sense that it's figuring out the next best word or whatever the thing is, picture or something like that, to put out. And one of the things we've been seeing from people at CVPR back in June from Tesla is that they are working on generative driving. So rather than reactive, it's actually sort of generating the expected next frame. So it's like, what is the next frame of time going to look like? And therefore, once it generates that, right, if it can generate 2 seconds worth of that, it can navigate within that world. And so again, if you can more efficiently create that and get closer to a better answer quickly, that gives you some really, really important leg up here. So wouldn't a quantum computer be good at this? That is, yes. The problem is that quantum computers are still pretty challenging to make. So
but the algorithm is designed for it. It's called Q.
Yeah, that's true. And also, of course, we got to have the real Q in there, like from Star Trek. So it's just funny that this is all sort of like cycling back on itself. Okay. Let's see if we got something else here. If you study logistics and heuristics at the oh gosh, so for the seed of an image. Oh, interesting.
Yeah.
Yeah. Okay. This is actually a good point here. So, Chris. Sorry. I'll get to yours.
No, go ahead. Do this one and do the one before that.
AI to date has been the equivalent to subconscious reaction, adding layers and letting a model think about what it's thinking is the next layer. Yes. So we're moving from the stochastic land of it just sort of repeating things that it understands people like to hear, to the level of it being able to be self-reflective. And self-reflection is massively important. That's like the kind of the major step to consciousness is self-reflection, and the ability to go like, was that the right thing to do? And then to learn from that and to do better in the future. So yeah, big point. Sorry. What were you saying, Scott?
Go to 106.
Yeah.
Comment at 106. Daryl Smith.
Daryl's? Okay. There's a lot of stuff.
Basically, he's imitating me. It's like some of my prose or some of my verse recently. Let's see if I get this right. But if you study the logistics and heuristics of the mystics, you will find that their minds rarely move in a line. So it's much more realistic for a man with such ballistics. Okay. Great job. I like that one.
That was pretty good. I like Daryl there.
It's really good. It's really good. Now, I'll be really disappointed if chat wrote that. Hopefully, he came up with it on his own. It's pretty good.
There you go. We just saw that whole thing. I sent you that thing about like the X in somebody's brain that causes them to be addicted to jokes, which was interesting. It was SpaceX. Yeah, Gödel Escher Bach, good book about a lot of things. Theory of mind. We are really getting to, I mean, I like that. It's Gestalt, I assume, in a way that you have to like think about Gestalt. But
Mhm.
we're getting to a point where the question of what does human consciousness mean is really becoming an important question. Like, is there anything special about our consciousness, or is it just emergent from these different factors that we're building? And if it is just emergent, then once we build a complicated enough machine, it's gonna have to have a consciousness, and that's kind of wild. So yeah, um, face purple crying. Oh, credit Brian Eno. That's cool. Okay, so I don't know if there's any other comments or questions from people, or Scott, what do you want to wrap a bow on this? I don't know if there is a bow. It's a scary bow.
Yeah, it's I mean, just think about how much everything changed since last weekend. Last weekend we were just talking about whether Sam Altman was going to be coming back in or not, and Q-Star was not on anyone's map at that point. And then what, Wednesday? I mean, right when everyone's going on Thanksgiving break, suddenly everyone's like, "What's this Q-Star all about?"
Yeah,
And
kind of crazy.
yeah, that means it seems to me it is quite groundbreaking and earth shattering. I mean, if you remember, see, what was it? LK-99. Remember, that was the big thing that dominated. What was it?
Oh
July. It was
yeah,
completely
yeah,
forgotten because it turned out that it panned out to be nothing.
right.
I have a feeling Q-Star is like everyone's going to say that. Okay, was that? Well, is that going to be the big November, December topic, or is that going to be the topic of
Right.
2023? So, yeah,
Yeah. I had to
it's
post
something we
this
have to
last night.
follow.
And since that whole joke about the Roman Empire came up and everything, I was like, so how many of you guys are thinking about Q Star every day? But yeah, it's just crazy because it was just what, 3 days ago, 4 days ago that this all happened.
It's only it's Saturday right now, right? It's like we
Yeah,
still have another day left in the weekend, and
I know, I
already
know.
we didn't have time to even look at it because it just popped up so quickly. And
And the funny thing is that all of this is based. There is a Reuters article, but this is all. Ben Shapiro has done some really good videos on this, and Explaining AI has done some good videos on this, and there's this paper. So everybody is building this entire castle on what could potentially not even be sand, but a cloud. So it might be completely stupid what we're doing here, but this is what happens, and it's exciting because even if OpenAI didn't do anything with this, I think this is a really interesting path, and giving more credence to this Q-Star paper would be a good thing, because I really think blending heuristics together, guiding search algorithms to get to solutions more quickly and more efficiently is a good idea. So, hey, Faye is a
and
Roman descendant. Nice.
yeah,
There you
and
go.
again, it kind of just goes back to my overall feeling decades ago of first trying to solve a lot of problems in geometric modeling and looking at it and just saying that when I see it as an intelligent being, it's just so obvious what the pattern should be or what something should be done. But
Right.
trying to turn it into some sort of step-by-step thing where you just don't have that overview of an intelligent being is extremely difficult to do. And I've always felt it
Right.
was like the missing piece in a lot of algorithms. So
Right.
now if you start taking these algorithms and start blending it in with like the intuition of it no longer is, again, when you're talking like Monte Carlo,
Right.
you would be going through a star and you come to a node and I have a bunch of different literal forks in the road. Which fork do I
Right.
take?
Right.
And you just roll a dice and say, let's try that one. And
Yeah.
you come to another fork in the road, roll the dice and try that one. And you roll the dice again, you do everything else. What you're now talking about is that when you come to that fork of the road, you just more or less have this like intuition or this feeling,
Right.
like this sixth sense of like, that's the road to take right there. I just know
Right.
that's the right way to go. And you
Yeah.
follow that and you follow that. And so and a lot of times you get that because you have that big picture feel as opposed to just only local knowledge where you know nothing about it. And again, a lot of us might say, you come to that fork of the road, you look on down there and you say, well, take the one that's the most well trodden. That's obviously the way to go because everyone's going that way. But
Right.
then again, Frost said, no, you come to the fork of the road, it took the road less traveled
Right.
because, maybe it turns out that's the way to go. So again,
Yeah.
you have to have this intuition of how to guide an algorithm efficiently. And if you can do that without, because again, you have an algorithm. An algorithm is a very clear way of going. The heuristic is like, well, we're going to apply some rules of thumb. So again, the idea with A star is that potentially you say, well, just calculate the distance as the crow flies between these things and know the kind of the direction and use that as a kind of a guiding principle. That's what the heuristic is doing. It's applying a rule of thumb, but it's just that it's a rule of thumb. It's still not super intelligent. It doesn't have intuition. And if you can take it to that next level, whew, man, it's like a neural net driven heuristics for algorithms will be something else.
Right. Right. Yeah. And I think maybe a good analogy to think about is that the Monte Carlo search is just a die, like 6-sided die. You throw it and it get 1 of 6. This is what you're doing is you're weighting that die. So you're not saying it's like you could weight it so that 6 comes up more frequently than the others, but it's not like it's impossible for 2 to come up or 4 to come up. So you're making it go that direction more frequently. So it's going to be better aligned. But so it's an explore, exploit. It's like you got to go out and explore things, and then you have to exploit the one that looks like it's the best. And what you're doing is you're reducing the amount of time you need to do the exploration, and you can increase the amount of time and efficiency of doing the exploit part because you can be more certain that you're going the right way. So yeah, it's pretty cool. So Alberta, hey, Faye is like all about Alberta. So, hey, I'll be flying through Calgary in March, by the way. So on our way to Vancouver. So, yeah. So anyway, this is really fascinating stuff. Again, I just want to be very, very clear. Scott and I have no inside information. We could be totally wrong about this stuff. We're pretty right about A-star, Q-learning, deep Q networks. That stuff is, established. But as far as Q-star and how it might be used and everything, we don't know. I'm really fascinated to find out. I really wish I could talk to somebody at Tesla AI because I would love to know if they're going like, Q-star for driving, interesting. Or whether they were like, oh, that's so March of 2023. That article is, we already did that. We included that, 6 months ago. So
and when did version 12 kind of start?
April. Oh, interesting. Yeah, I think that was March, April. I think that was no, I think it was actually even earlier than that. So there was a beginning of it, but then I think it got greenlit in somewhere around March or April, if I'm remembering Walter Isaacson's biography timeline.
Yeah,
could be wrong.
Yeah, exactly. That. So maybe there was some breakthroughs that allowed them to do that. So it's like that's not an obscure paper. It is to us, but to anyone in the AI community, they would.
No, exactly. Yeah, it's one of those things where I think part of your job being in that community is that you just have to keep up with this stuff, or somebody does. If you've got a team of 35 people, one guy's like, oh, check this out. I just read this over the weekend. And you're like, cool. So, it gets distributed. If only 1 out of 35 people sees it, then everybody has access to it.
But just that title alone, when it said, A-star without expansion, I'm like, whoa, wait. I would be intrigued enough at that point that didn't have to read the rest of the title to say, yeah, that's something you need to go into and investigate. Yeah,
and it is fascinating. And like I said, as soon as the stream is over, I'll post the link to it in the description for this video so you can have it, because it's well worth a read if you're into that kind of stuff. It's really interesting, really cool. A good paper too. So I always like well-written papers. Cool. Well, thank you, Scott. This has been interesting. I hope people have enjoyed. And obviously for folks who come in afterwards, read the comments as you're able. There's some really good comments in there, and sorry if we didn't get to all of them. I'm going to get a third person eventually just to sit and look through comments and post them for us. But anyway, all right. Well, everybody have a great afternoon, and go follow Scott on, that's what we need is Grok to be sitting in here and reading the comments and ferreting them out. But anyway, so follow Scott and me on X and on YouTube, and we will see you guys in the next video. And hopefully the stream will end when I do it. Hopefully this was an okay first stream on StreamYard. Let me know. Anyway, all right. Cheers. Bye-bye, everybody.
Bye.